So thank you very much, Miguel and Belen, for the introduction. And of course, thank you to the organizers for inviting me to this very nice online workshop. So we've had several topics already on this, several talks already on this topic, also yesterday and the other days about these correlations. But specifically today, I will try to give some context to the calculations Belen just showed, introduced before. But let me do a more general introduction. So over the years, I've been working on few body models with coupled channel methods to describe the structure and reactions of three-body nuclei. And in particular, we know that two neutron halo nuclei are a very good example of these cluster structures because they are Borromean. So when we start from a core and we add one neutron, we end up with an unbound system, but then a second neutron brings some stability that allows these very exotic nuclei along the dripline to be bound. So we know it's clear for us that the interaction between the valence neutrons is key in binding the system. And many times we speak about dineutron correlations or dineutron configurations, which depend essentially on the mixing in the wave function. But when we go beyond the driplines, we may find structures that resemble that of Borromean halos, but laying totally in the continuum. So in that sense, that's what we call these true nucleon emitters, such as beryllium-6 or beryllium-16, as Belen discussed before. This is a 2-proton emitter or a 2-neutron emitter. And of course, there are many others, for sure, many others to be discovered. So to be more specific, although we have already seen this before, we speak about 2 nucleon emitters in the original sense for 3-body nuclei, these 3-body nuclei which lay totally in the continuum. They are unbound with respect to 2 nucleon emission, but bound with respect to 1 nucleon emission, such as beryllium-16 or beryllium-6. And this means that we expect this decay to proceed directly because the sequential decay is mostly energetically forbidden, although some sequential decay will be possible because these states are broad. In any case, the naive picture is that this direct decay will be enhanced or favored if we have strong dineutron correlations in the initial state. But as we've been discussing, this link between dineutron or diproton in the initial state and sequential or prompt decay is not clear at all, especially when we consider excited states. And well, the case of 2-proton decays has been studied more, let's say. The case of exotic 2-neutron decays is newer, let's say, and I will focus on that. So we have this example for beryllium-16. This is the data that Belen already presented by the MSU measurement. So here in this experiment, they measured the beryllium-16 spectra by doing 1-proton removal from boron-17. And this structure was assigned for the ground state of beryllium-16 here. And from the energy and angular correlations, they assigned this sort of dineutron-like nature to the decay. This was a bit controversial at the time. I'm sure Miguel knows the details, but I will not explain too much about it. But now we have new data, the one that Belen presented, so we will discuss about these things. And well, from the theoretical side, there are many works on the field. Now it's a very hot topic. But these two, I think, are particularly interesting for the calculations I will present today. Actually, this work by Amy Lovell and collaborators is the one that inspired me or pushed me to focus on this topic, because I saw the possibility of applying our methods, the ones that we use for reactions, to explore these 3-body decays. So this was 3-body true 3-body scattering calculations for beryllium-16, and analyzing the eigenphases, they obtained this ground state resonance with a given width, and they also assigned a very clear, well, they also observed in the calculations a very clear dineutron configuration. Then we have also this very, very nice and interesting work by Simil Wong and Vitek Nazarevich that we had the chance to learn about yesterday, using a time-dependent approach for the decay of beryllium-6 and beryllium and helium-6. And well, in a sense, my calculations lie in between these two, because we use these 3-body methods, but I also use a kind of time-dependent evolution. And there are many other works like those by Grigorenko. These are only a couple of examples. And there is also the works by this group in three-body decays. And in general, all these works have use very different techniques. So the way I see it, I think there is, the problem is very open for discussion. So now going to our calculations. So this is the kind of three-body models that we use. So we use the so-called hyperspherical formalism in using Jacobi coordinates in the t and y representations, but I will focus on the t representation here today. So we have the wave functions of the system expanded in this way in using hyperspherical harmonics expansion. The hyperspherical harmonics are very well-known analytical functions, which are eigenfunctions of the hypermomentum operator. So we have this k, this hypermomentum, which is a three-body quantum number. And to get the wave functions, we need to solve this a set of coupled hyperradial equations involving some coupling potentials. These coupling potentials contain in general the binary interactions between the particles and possibly also a three-body force to fix the position of the three-body states. But what is interesting here in this equation, I think, is that you see that in three-body systems, we have an effective barrier, which is a sort of effective centrifugal barrier, which is given by the hypermomentum. And even in the cases where we have k = 0, k = 0 would mean zero angular momenta relative between all these particles, we have an effective barrier. And these are genuine three-body dynamics, and this may have an influence on the final decay correlations. And I will come back to this later. So in principle, one could solve this equation with the proper boundary conditions for bound and continuum states. And it can be done, but it's a bit computationally expensive for continuum states. And it's not always easy to interpret the results. And for many years, we have been using a different approach, which is very convenient for reaction calculations. So we wanted to try this also here. So we use the pseudostate method to describe these wave functions. That means that instead of solving these equations with proper boundary conditions, we diagonalize the Hamiltonian in a given basis. And this leads to an eigenvalue problem. We have in general, we will get some negative energy eigenvalues representing the bound state and some positive energy eigenvalues that represent the discretized continuum or a discrete representation of the continuum. To do this kind of approaches, you can use the basis that you want in your expansion, but I'm from the Seville group, so we use the analytical transform harmonic oscillator basis, which has a very nice analytical properties, although I will not discuss the details today. So at the end, once we solve this Hamiltonian, we get something like this. It's an example for helium-6. So we will get for 0+, 1-, 2+, etc. states, this kind of spectra. So for helium-6, we have a one bound state and then some representation of the continuum for the 0+, and the same for the 1-, 2+, etc. This representation is very convenient for reaction calculations because, for example, we can explain excitations into the continuum or breakup as inelastic excitations because all these states behave like bound states. They don't have the proper asymptotics. But when we want to describe resonances and decay properties, this is not very convenient because resonant behaviors is hidden here in this spectrum. So before studying the correlations, a couple of years ago, we proposed, because we wanted to keep using this simple approach because it's very conceptually, it's easy conceptually and also computationally. And we proposed a method to identify and characterize three-body resonances using pseudostates. So the idea is that, for example, in helium-6, we have here, we know there is a quadruple resonance here and no dipole resonance and no energies. And in this spectrum, it's not easy to characterize the properties of such a state. But we know that resonances are very sensitive to changes in the potential, and the probability of a resonance is strongly concentrated at short distances, similar to a bound state, whereas non-resonant continuum states are spatially spread. So we propose that we can identify resonances in this pseudostate representation by obtaining the eigenstates of this operator, which might look fancy, but it's not. So this is simply the potential energy operator averaged by the energy. And we propose that resonances should be obtained in this kind of approach by eigenstates of this operator corresponding to very large and negative eigenvalues. And we obtain these solutions by expanding precisely in energy pseudostates. That means that we have like a two-step diagonalization to build the resonances. And when we apply this to the example of helium-6, this is the result. So we know that there is a quadruple resonance here. And when we do this procedure, this is the kind of spectrum we get for this operator, where for the 1- state, we have essentially non-resonant continuum. But for the 2+ states, this operator allows us to separate the continuum in 2 regions, one for the non-resonant continuum, and here we have a state which is the 2+ resonance. And since we expand these states in all these energy eigenstates, we can build energy distributions. And from these energy distributions, we can assign resonance energy, width, and other decay properties. So this is what we did for, you can have all the details here. We published this a couple of years ago, so I will not go through the details unless you have questions. And we applied this for beryllium-16 before we started this collaboration with Belén and Miguel for the new data. So this was a resonance identification for the ground state of beryllium-16, and this is the typical convergence plot that we used to see, that our ground state is well converged with a number of hyperspherical harmonics in the three-body model. And by analyzing the energy distribution of this state, we could assign also a width to the state in very good agreement with the true three-body scattering calculations of Emil Lobel and collaborators. So this was a very nice benchmark result. And we also obtained this very nice figure that Belén already showed in the Jacobiti representation when we have this strong dineutron configuration. This was also in good agreement with Emil Lobel's work. And most interestingly, before this new data arrived, we also were able to predict a 2+ resonance. So before this state was known, by doing the same analysis for the 1- and the 2+ states, we obtained this prediction for the 2+ spectrum, finding a possible resonance around 1 MeV above the ground state with a much larger width. And this was very nice because, as Belén just showed, this was later has been confirmed experimentally, although this hasn't been published yet. So we know from the data that Belén presented before that the beryllium-16 is consistent with these 2 states. So we have the ground state and the excited state. I don't know if the energies are correct. Maybe these are not the last one, but and they are close to this.
Yeah, more or less.
Yeah, okay. And we were interested in studying how these states decay, because in principle for the 2+, we could have also sequential decay, as Belén mentioned. And looking first at the initial wave functions, we observed these very nice distinct spatial distributions in which for the 0+ we have a clear dineutron or dominant dineutron peak, whereas for the 2+ we have almost no special correlations. And now the question was, can we explain from these initial states how what we see in the final relative energy distributions in the decay? And to do that, we took a step forward in our approach. So what we do is we take our resonance wave functions that we have obtained with this identification method, we time evolve these wave functions, and we perform a sort of matching with the asymptotic behavior, including incoming and outgoing waves. And essentially, since asymptotically only the outgoing waves survive, these coefficients in the matching determine the final relative energy distribution. This is a work in progress. I will give you some details in the next slide, which is the last one. But these were the plots, the figures that Belén presented for our preliminary comparison between this three-body model and the data. As we have already seen, we have a very nice reproduction of these low-lying correlations, and we see that this peak for the 2+ is much narrower. Now, the question is if we are able to understand why this is happening, because naively we would expect the opposite, right? And to go to that, and maybe I don't know if we will be able to answer some of the questions that arose before, let me show you how we build these distributions. This is not 100% accurate, but more or less I think you can get the idea of how we build these distributions. So in this three-body model, the final relative energy distributions are related with a hyperangle, which is one of these variables in the hyperspherical formalism. So our distributions look like this. Which of course involve some mixing between different components of the wave function. And we have here these hyperspherical harmonics for different hypermomenta, weighted by these asymptotic coefficients that we have in the matching when we study the time evolution of the state. And well, these functions are essentially Jacobi polynomials, but it's just technical. Now, what we see in the calculations is that apparently, as time evolves and we get these final asymptotic coefficients, the components of the wave function for the lowest possible hypermomentum values increase with respect to the original ones in the initial state. What that means for beryllium-16, for example, our wave functions are dominated by hypermomentum equals 4, which is related to the fact that we have strong D waves in these states. But then asymptotically, we see that the coefficients for the k equals 2 and k equals 0 components become larger and comparable with the dominant one in the initial state. So what we see in the correlations, it seems like this is essentially the interference between the hyperspherical harmonics with k equals 4, 2, and 0, which in the fact that the k equals 0 contribution is symmetric gives this more symmetric shape for the 0 plus as compared for the 2 plus. And this is because for the 2 plus state, the k equals 0 term doesn't appear in this function. Just because of angular momentum conservation, the minimum possible hypermomentum for the 2 plus state is 2. So the symmetric contribution in the distribution doesn't show up, and we have the interference between k equals 4 and k equals 2, and so we have a much more asymmetric peak here. Of course, here the energy also plays a role, because if you have a high energy, you can build these correlations. So while if the energy is very slow, it's very small, you cannot build these mixes. But anyway, I think we understand from this comparison of the coefficients for both states that this comes from the mixing of the different possible hypermomentum. And this is related to what I said before, that is related with the effective barrier for three-body systems. The fact that for the 0 plus and the 2 plus states, the neutrons have to penetrate different barriers with different heights, produce this different in the distributions. And well, this is what I had prepared. I have maybe more material, but we can leave that for the discussion in case something comes up. So I think I'm already over time. So this is conclusions of my work. So I have tried to give you some context about these three-body calculations for the decay of 2 nucleon emitters. Well, 2 neutron emitters, I would say, because it's the thing I discussed today. Using this pseudo-state representation, that is a very simple bound state method if you want, but extended to describe this continuum. And I have shown you that the final correlations that we observe in the decay of beryllium-16 seem to be related with this interference between the different hyperspherical harmonics that we have in the wave functions, which are different for the 0 plus and the 2 plus. All this work is, I must say, preliminary. So we are now exploring different effects, different things. So in particular, I would like to see what is the effect of the strength of the neutron-neutron interaction, and also, more importantly, the effect of Pauli and Korb excitation effects in the final decay distributions, because I think this perhaps would give us more information to understand the full picture. And well, these are the collaborators for this work and the funding agencies that allowed this project to be followed. And so I would like to thank all of them, and thank you for your attention.
Thank you very much, Jesus. I think you gave a lot of answers already. But if there are a few short questions, Olivier?
Yeah, thank you very much for the very clear talk. My question is that I'm surprised that the 2 plus of beryllium-16 doesn't decay sequentially to the 5.5 plus unbound state, because it has L equals 0. So it has no centrifugal barrier, so usually it's favored. So my question is that, do you also estimate the branching to the sequential decay as well? Can you know why it would be favored for the 2 plus to decay by 2 neutrons, despite it can be very easy to decay by 1 sequentially?
Yeah, I see. Well, at this point, I think we don't have yet the full picture, in the sense that we have computed only these neutron-neutron correlations, in these decay correlations, and not the fragment neutron correlations, which of course are also there in the model. So I hope that we will have the full picture soon. Maybe that can give us some information about this. In any case, following the philosophy of the talks by Simin Wan yesterday, I think the proper way to understand this sequential or direct decays is to do the full tracking of the time evolution. So looking at the wave function and see how it evolves, this neutron correlation in time. And hopefully we can do that too. So I think we are describing similar phenomenology, similar qualitatively results here, using different models, which is good. And I hope we will have the full picture to compare both approaches soon. I don't know if this answers your question, because I mean, yeah, I cannot really say why we see at this point direct and not sequential in this case, but I hope I will have the answer at some point.
Okay, one short question of mine. So technically, you can you can apply exactly the same model to the proton-proton case.
With some with some caution, because there are a few technical things here. The first is that the way we identify the resonance with this approach has been tested only for neutral systems, because to describe this operator from a variational principle, it should be purely attractive. So when you have repulsive terms, I mean, it can work, but we haven't tested that. So
Okay.
we will see. And then from the point of view of the asymptotics, then of course, when you have the Coulomb, everything becomes a bit more complicated, because here you need Coulomb functions, and the convergence is much more complicated. So we should see if we are able to get some asymptotics. But it would be nice, yes, to have the full picture, of course.
Oh, I'm happy with the neutrons already. So
Yeah.
Okay, so if there are other questions in the audience, we will be able to discuss at the end of the two sessions. So thank you again, Jesus. And then we move to the last talk before the break. Aldric Rebel will talk about other interesting cases in two neutron decays. Okay.
Can you hear me?
Yeah.
Sorry.
Go.
All right. Good afternoon, everybody. So yes, I slightly changed my my title compared to the one that was announced previously after discussing with organizers. And so I will talk today about like observation of two neutron narrow resonances close to threshold. And the question will be if we see in this case a generalization of the Akeda conjecture. So since the beginning of the week, we saw this diagram several times already about the Akeda conjecture that postulate that we should basically see an alpha cluster states close to or in proximity to the corresponding alpha threshold, and the most famous one being the Holt state in the carbon 12. And so some time ago, I mean recently, it has been proposed to generalize this conjecture to other cluster, such as two proton and two neutron clustering effects. And here's a figure from Okolovitz and collaborator, where we see not only the oil state, but also narrow resonances in lithium-11 for two neutron case and for neutron case. And in fluorine 15 that was presented by Valerian in the beginning of the week. And so basically, when we move to two neutron two neutron resonances, we from two proton one, we basically hope to be able to have a better picture of what is happening in the nuclei by the fact that the Coulomb barrier is not doesn't play a role at all in this case. But we are confronted to some other difficulties in case of neutron, simply because it's a neutral particle, and then it makes its detection quite difficult. And we suffer from usually low efficiency detection, and we actually have to detect it indirectly, usually by proton scattering in plastic scintillators. And this also makes extraction of neutron-neutron correlation at low energy not that trivial. But the good news about this is that this can be improved by technical developments. And so in order to look at such narrow resonances in proximity to two neutron threshold, many experiment has been performed in the past, let's say, decade or so, maybe a bit more. And such resonances have been found in different kind of system on neutron nuclei. For example, in such as a beryllium-16 that Belen was mentioning. So other systems similar to it that are unbound by two neutron, but that for which there is no available intermediate resonances in the decay in the intermediate nuclei, so in the A-1 nuclei, if you want. So, for example, so barium-16, such as Belen presented, but also lithium-13 and oxygen-16, which is very famous. And in this case, we don't expect to see any kind of sequential decay of the two neutrons, but more direct two-neutron emission. And we, of course, want to study eventual correlation between those two neutrons that are emitted. Other cases are Borromean nuclei, such as beryllium-14 that Belen mentioned, but also I will show some preliminary results about fluorine-29. And other kind of nuclei that are, in this case, I want to show some results about fluorine-28, which has been studied in the same experiment that was presented by Nakamura-san, but this time the two-neutron decay channel. So toward fluorine-26 and 2 neutrons, and which is a 1 neutron bound nuclei, but for which we populated high energy resonances that are located above the 2 neutron emission threshold. So in order to study all those cases, similar experimental setup were used, and here I just take as an example the one that was used in RIKEN for the oxygen-28 experiment, where basically we have a beam coming to a target where we perform a knockout reaction most of the time, and we populate nuclei of interest, and sometimes excited states in the nuclei that will decay by the emission of 2 neutrons, and those 2 neutrons are detected in some neutron detector. In case of Samurai, it's usually nebula, but for oxygen-28 campaign, NEULAND was also used, which is now back in GSI. And we also detect as a fragment. So in this case, I took example of fluorine-28, so fragment being fluorine-26. So using this kind of setup, we have access to the full kinematic of the decay. So the momentum of the first neutron, momentum of the second neutron, and the momentum of the fragment. We can reconstruct using the invariant mass method the energy of the system, and that allows us to perform the 2 neutron unbound spectroscopy of the nuclei populated. And we can also look at the decay mechanism of the three body. So usually we compute those epsilon nn and epsilon fn variables that can be understood basically as a fraction of the full energy, the total energy which is taken by the 2 neutrons for epsilon nn, or by the fragment plus 1 of the neutron for epsilon fn. And of course, we want to have as much statistic as possible and the best resolution possible. So now that we have populated the state, they will decay, and mainly 2 types of decay can occur. So direct decay, like I saw here on the top left, where the 2 neutron will be emitted simultaneously. And in this case, we expect to have some phase space modified by some neutron-neutron correlations. And here in the bottom, I show what this can look like in case where we consider S-wave, as it was discussed by Belen, where I use in this case this simple model where we can link the epsilon nn amplitude at low, the signal at low epsilon nn to the relative neutron-neutron distance of the source considered. And so this is what signal we expect for such a direct decay in case of S-wave. And for sequential decay, where our resonance is going to decay by the emission of 1 neutron to populate a resonance in the intermediate nuclei before to emit a second neutron, we expect in the same data plot some ridges along the EFN, so meaning some favored energy between the fragment and 1 of the neutron, that correspond to one gap or the other, one energy gap or the other between one of the 2 energy gaps between the 3 different resonance populated, so initial state, intermediate resonances, and the final state in the A-2 nuclei. And so here I show an example of some results that we published a couple of years ago about carbon-18 that we populated by a deeply bound proton knockout. And in this case, we were able to populate very high excitation energy states above the 2 neutron emission threshold, which is in case of carbon 18 at about 5 MeV. And also we didn't clearly see, due to resolution, narrow resonances in proximity to the threshold. We were able to observe a wide range of relative energy above this 2 neutron emission threshold, up to 15 MeV above the threshold. And basically, because we didn't see any kind of discrete structures, we decided to slice this energy range in different sections, and we studied correlation in each of the sections and compared those results as a function of the decay energy, basically, on a very wide range. And so in this case, we show, here's the result in the middle. So where we, for one of those sections, but they are all equivalent, like I will show you in the following slide, they're all very similar. We observe a very strong signal at low epsilon NN, which is a signature of a very the emission of two very correlated neutrons. And we don't see any kind of sequential signature from sequential decay, which somehow can be kind of surprising in a way that there should be a lot of resonances available in carbon-17 in that whole range of energy. So here's a result for the whole range of energy considered. So as I said, we did like more or less 4 slices in this wide range of energy. And the boundaries of the energy range slices are from 0 to 3.7 MeV, and 3.7 to 5.3, and 5.3 to 7.2, and 7.2 to 12 MeV above the 2 neutron emission threshold. And those energies were chosen to have similar statistics in each sections. And what we see is that, so on the left is experimental data, and on the right is a result from simulation using the simple model from Lednicki and that Belen mentioned. And we could extract from this the RMS relative distance between the 2 neutrons in the nuclei before decay. And we found something at around 4.1 MeV, which is and we also saw that this value was similar for every section. So we didn't see any kind of strong dependence from the different decay energy considered. Even if by eye, it seems that the signal seems bigger and bigger as we go high in energy. And this is an effect that I just wanted to discuss a bit, because it's quite, it's an effect that becomes even stronger when we go to low energy resonances. So here in the bottom right corner, I show different simulation for some, so from epsilon NN for different region of decay energy considered, from 0 to 0.3 MeV, 0.05 MeV, and 0.21 MeV and 0.2 MeV. And we see that even if I consider the same relative distance between those neutrons, the signal seems to collapse the lower in energy we go. And this is partly explained by the fact that this epsilon NN variable is defined as the energy of the 2 neutron divided by the total energy. And since the total energy become lower and lower, this kind of spread out the signal, or another way to see it is that when we go to high energy, the signal get pushed to the right and seems to go higher, or at least to come out visually better. But this also due to low energy to other effects that are linked to the detection of the neutrons, especially crosstalk rejection algorithms and so on, that basically cut low energy part of our accept. I mean, effectively cut the very low energy part of our spectrum, but is especially strong for epsilon NN small in this region. So we can see in the red curve, we have a strong cut of the signal, which is not only due to this effect of total energy considered, but also on this crosstalk rejection algorithms. And so, as I mentioned, there is many, several systems for which we observed low energy, narrow resonances in proximity to 2-neutron emission threshold. So one of the systems is lithium-13, which is somehow kind of similar to beryllium-16, as it's a 2-neutron unbound nuclei for which the lowest resonance available in lithium-12 is at about 210 keV. So in this case, we don't expect we cannot see any kind of sequential decay. We expect pure direct decay. And this resonance at 120 keV, which is very, very low energy, has been studied by Collier and collaborators from the MONA collaboration. And they found some signal consistent with some d-neutron configuration by opposition to Seeger-like configuration, which is very similar to what Belen just showed for beryllium-16. Another case was oxygen-16 that's been discussed a lot, is a very low energy resonance at about 18 keV, which also in case of oxygen-25, the lowest resonance available is at 750 keV. So we cannot see any kind of sequential decay, and we expect a direct decay in this case. It's been predicted by, so it has been studied by Kondo from Samurai collaboration, and it has been predicted by Hagino and Sagawa that in case of oxygen-16, we should observe some Seeger configuration in the correlation of the two neutrons. However, this is a very challenging task to study, as in this case, the three bodies, so the two neutron plus the oxygen-24, are sharing only 18 keV, which, because of the boost of the beam, makes, in case of neutrons, makes them in the lab frame arrive in detectors with a very small relative angle, which makes it very tricky to detect or at least distinguish because of crosstalk problems. And so an experiment has been approved, like Nakamura-san mentioned in his talk, to dedicate to study source correlation using new generation detectors with very high granularity at the Samurai. And so now I move to some preliminary new results from the oxygen-28 experiment, where fluorine-29 was populated through a knockout reaction, and we could observe its decay toward fluorine-27 plus 2 neutrons. And here I show the spectra from Julian Karboff that is in charge of this analysis. And we see here that we observe several resonances that are well resolved, but in particular, we observe one which seems very narrow at about 300 keV from the 2 neutron emission threshold. And if we place this in the decay scheme, this places it about 100 keV above an available resonance in oxygen-28 that has been observed in the same experiment. And in this case, we cannot conclude on the correlation between those three bodies because of statistics issues, since we have a very strong contribution from uncorrelated background that has to be taken into account in this area. And so it's hard to distinguish if those three body decays through a sequential decay or some direct decay straight to the ground state of fluorine-27. Another case that has been studied in the same experiment by me this time is fluorine-28, which is basically, so Nakamura-san earlier showed the 1 neutron decay, but we could also populate higher excited state resonances that above the 2 neutron emission threshold that decay by the emission of 2 neutrons toward fluorine-26. And in this case, we can reconstruct this relative energy spectra, where we also see several resonances that are like well defined, and in particular one which is very narrow and close to threshold at about 240 keV. In this case, even if the unbound spectroscopy of fluorine-27 has not been performed yet, it is believed from preliminary analysis that there is no resonances available in this area. And we therefore expected some kind of direct decay, at least no sequential decay. And here I show in the bottom right preliminary result for neutron-neutron correlation, so epsilon NN. And I put in red the phase space as a reference. And it seems that we have indeed some signal at low epsilon NN in this case that would again push us toward a conclusion that we have some so-called dineutron decay by opposition to Seeger-like decay. It is interesting to notice also that this particular resonance has also been observed to decay by one neutron neutron decay, which is somehow make it kind of similar to the talk from kind of similar to fluorine 15 that was discussed by Valerian earlier this week, where also you had some 2 proton resonances that were also observed in the 1 proton decay channel. So to summarize, I believe we entered some new era of high statistics and high resolution in those multi-neutron decay experiments, thanks to a very strong development from the community on beam intensities, use of a thick liquid hydrogen target, as it was the case for the oxygen 28 experiment, but also on the beryllium experiment, for the beryllium result that Belen showed, that both contribute to the increase of statistics and resolution, and also development of new neutron detectors with bigger volume and high granularity, like the case for Hime, for example, in Samurai, which will be very helpful in order to study correlation of very low energy resonances, such as in the case of oxygen 26. This allowed us to observe clearly multi-neutron unbound resonances, and we found, like it was the case in, for example, in fluorine 28 here on the side, but also for many other cases. And we can, by studying the three-body correlation for a given resonance, because now we can identify resonance clearly, we can gate on one of them and look specifically at the correlation for this precise resonance. We can distinguish direct and sequential decay. So here in the case of fluorine 28, in red, we have the correlation observed for the low energy resonance, but if we get at around 2 MeV, where we have also the resonances, and we look at those correlations, we see a strong signal, which is typical of a sequential decay, where we have those ridges along epsilon FN. But similarly to the talk from Bob Charity, where you could observe both signature of direct and sequential decay in 2 proton decay, we also see some signal at low epsilon n in this case. So of course, all this is preliminary and it's in the work. It's in progress. And of course, we saw also that neutron-neutron correlation are very challenging for low energy resonances. But most of all, I think the very important point that I wanted to show today was that in the vast majority of cases, if not all cases, we see the similar kind of correlation, meaning systematically correlation that are displayed at low epsilon nn, and which could show that we are dominated by S wave configuration. But of course, I think that's one of the big questions, to know how to observe the other configuration, or why don't we observe them. And so what's next? So briefly, there's going to be future experiment dedicated to neutron correlation, like I mentioned. So in case of oxygen 26, which is a proposal from Nakamura-san, where he's going to use a Hime, which is a high granularity neutron detector, but also multi-neutron 4-neutron correlation experiment, where it will be interested to see if those states decay by the spontaneous emission, by the emission of 4 neutrons simultaneously, or 2 neutrons at a time, or in some kind of a democratic decay of 4 neutrons. In case of oxygen 28, from what Nakamura-san mentioned, it seems that it's more the case where 2 neutrons are emitted toward the ground state of oxygen 26 and then 2 other neutrons toward the oxygen 24. And there is another experiment that has been performed by the group from Miguel on spectroscopy of hydrogen-7 decaying toward the tritium plus 4 neutrons. In this case, we have a very high statistic of about several 10,000 of events for such correlation, meaning several tens of events in which we detect both the 4 neutron, all particles, so 4 neutrons plus the triton. And so that is it for me. So thank you for your attention.
Okay, thank you, Aldrich, for this overview of many interesting cases at the threshold. But we are running out of time. We are already 15 minutes late. So if there is no urgent question, I propose that we shift the discussion about Aldrich's results to the discussion session at the end. And then the break was supposed to end at 3:50. So we can shift it by 10 minutes and we go back at 4 p.m. So then I thank all the 4 speakers of the session, and let's go back to the workshop at in 15 minutes at 4 p.m.